So we will start by discussing the first mechanism of charge transport, which is drift. If you consider an electron or a hole, it's a particle in space, and this particle, if it is free, is going to move. The first kind of motion we can imagine for holes and electrons is something called thermal velocity or thermal speed. There is an amount of thermal energy in the system equal to 3/2 kT. This is going to be translated into kinetic energy for electrons and holes. Of course, when we calculate the kinetic energy, we're going to use the effective mass of electrons or the effective mass of holes in the calculation. From this, we can get a value for V thermal, which is the thermal velocity of an electron or a hole. This is usually a very high value. It's actually 2 orders of magnitude lower than the speed of sound. So electrons and holes are moving at a very high speed within the crystal, and this is for value of temperature equal to 25 Celsius, so room temperature. So this kind of velocity does not participate to current flow. It is not a charge transport mechanism. We are interested in mechanisms that allow charge to be moved from one location to another in a net manner, because this is what gives us current flow. The problem with thermal velocity or thermal speed is that it is a Gaussian process. It's a normal process. It is a random process, and it has a zero mean. So yes, it can move in this direction at a very high speed. However, it's going to move in a different direction shortly. It's going to move in a totally different direction after that. It's going to keep going like that, and the net result is that it isn't moving. It is remaining at its original position, in effect, because all of these thermal velocities will cancel out. So there is an instantaneous value for thermal speed, but there's no net value for it. So the particle is moving, but it's not carrying current. What does it produce, though? I mean, if it's moving, it has to produce something. What it is producing is noise. This is the major source of noise that we have to deal with. If, however, we have an electron and we subject this electron to an electric field, then this electron will move against the electric field. It will still move using its thermal energy in a random motion, but there will also be a component added to it that causes it to move a net displacement against the electric field. This is the velocity we are interested in, and we call it drift velocity. This is the velocity we are interested in because it is directional, because it is a net velocity that causes charge to move from one location to another, causing current to flow. So what we need to do now is to calculate the drift velocity and understand drift as a mechanism of charge transport, because it will be one of the two major mechanisms of current flow that we will consider. To calculate drift velocity, we have to understand that electrons do not move in a smooth manner in this way. Electrons are actually not moving in vacuum. They are moving within a silicon crystal. So what happens is that they sometimes bombard with something or hit something, and there are collisions as the electron is moving. And so if we try to chart with time the drift velocity, the actual drift velocity that we observe, the magnitude of drift velocity, you'll find that it increases, and then a collision happens, and then it drops, and it keeps increasing again, and then it drops, and so on. So I mean, of course, not every time would the electron make a collision at the same level, but more or less there's an average level of velocity at which the electron makes a collision and then comes to a complete stop, after which it starts to accelerate again. Why does it accelerate? It accelerates because it lies in an electric field. The electric field imposes a force upon the electron, and the force will cause it to accelerate. This is Newton's law. So it will accelerate. If it were in vacuum, it would keep accelerating forever. It is not in vacuum, so it will collide. Actually, it normally collides with an impurity atom, because it is the irregularity in the crystal that we have, and it comes to a complete stop. Again, we are not going to see it coming to the same level every time. It's going to maybe travel a little longer this time, a little shorter the next time, but there is some kind of average level that we should be able to find. The statistics that characterize this kind of motion are the amount of time that the electron manages to accelerate before coming to a complete stop. We call this time tau free, or the mean free time. It is the average amount of time that the electron can move without making a collision. So the other factor that we have to calculate that we are interested in is the final velocity that the electron reaches before it comes to a complete stop. So when the electron moves, its final momentum before it collides is going to be me times v final. This is its final momentum, its highest momentum before it makes a collision. We also know that momentum is equal to force multiplied by time. And so the final momentum is also going to be the force that the electron is exposed to multiplied by the mean free time. These two are going to be equal because this is the momentum that the electron has gained from the force, and it is the momentum that it has gained through its final velocity. We also know that the force is equal to minus Q times E, the electric field, because that's what an electric field does. It imposes a charge upon, it imposes a force upon a unit charge. Now, equating the two values for momentum, we get me times v final is equal to Q times tau free times E, the electric field, right? And so, of course, here we are ignoring signs because we are just using absolute values, and this allows us to get a v final, a final value for velocity equal to Q tau free divided by me times the electric field. If we had used the sign, the negative sign, all that would have indicated is that the velocity is in the opposite direction to the electric field, which is something we know is true for electrons. Now, v final is the final velocity we reach, but if we want to consider the electron moving at a constant speed, then that constant speed is not the final velocity, it is actually the average velocity. So we're going to divide the final velocity by 2 to obtain an average drift velocity, v drift. And so v drift is going to be Q tau free divided by 2 me times the electric field. Now, this is describing a relationship between the velocity of an electron and the electric field that the electron is put in. And it is suggesting something very important. It's suggesting that the velocity of the electron is directly proportional to the electric field. So if we draw the velocity versus the electric field, we will obtain a straight line whose slope should be interesting. The slope, or the constant of proportionality, is all of this. And what do we call it? We call it mobility. And so this is the mobility of the electrons, mu n, which is equal to Q tau free divided by 2me. So it is a function basically of the mean free time, as well, of course, as the effective mass of the electron, but that is more or less a physical constant. So it is, the mobility of electrons is a function basically of the mean free time. What is the mean free time? It is the amount of time that an electron can flow through the crystal without colliding. And what affects mean free time? What affects it is basically impurities in the crystal. The more the impurities, the more often the collisions, and the shorter the mean free time. So the higher the doping, the lower the mobility of electrons. This linear relationship between electric field and drift velocity for electrons is extremely important and will be the basis of all of our derivations in Module 1. In Module 10, we will discover that this relationship has severe limitations. If we draw the same relationship for holes instead of electrons, we'll find that it is still a linear relationship because there will be nothing different about the whole derivation. The main difference will be that we could probably see a different tau free, but that we will definitely see a different effective mass. So we see a different effective mass for holes from the effective mass for electrons. The effective mass for holes is larger than the effective mass for electrons, and therefore we can always assume that mu p is smaller than mu n. The mobility of holes is smaller than the mobility of electrons, because holes are actually electrons in the valence band which are trying to move, and the valence band is really crowded, and so they move a lot. The motion for them is a lot more difficult. For most of our work, we will assume that mu n is approximately equal to 2 mu p. This is not always true. The specific values depend on the specific values of effective mass and also depend on doping. So this is an approximation, but it is one we will often make.